Hello students, welcome you all. In my today's lecture, I will tell you the structural elucidation of is cholesterol. In my last lecture, I told you about the introduction, nomenclature and stereochemistry of the steroids. So let's discuss this structural elucidation of is cholesterol. Now, the structure of this cholesterol, it is like this. This is first ring, second ring, third ring, and this is 5-membered fourth ring. Okay, now here we have one of the angular methyl group. These are the two angular methyl group, and this is the another side chain. Okay, so and here it is cholesterol, as the name is cholesterol, estrol or esterol. So it contains one of the secondary OH group at this position, and suppose I write here, this is suppose 5-beta cholesterol. Now let's give here also this hydrogen is below the ring, here this hydrogen is above the ring, here hydrogen is below the ring. Now this is the structure of cholesterol, and let me name it. So if I name it, then this is our first position, this is second, this is third, fourth, fifth, sixth, seventh carbon, 8th carbon, and this is 9th one, this is 10th, okay, 11, 12, this is 13, 14, 15, 16, this is 17, okay, this is 18, this is 19, this is our 20, 21, 22, 23, 24, 25 and 26. Sorry, this is 25, 26 and this is 27. Okay, so 27 carbons are present in a cholesterol, and one of the double bond is also present at 5th and 6th position. Okay, so this is the structure of cholesterol, and if I write, then this is our ring A, this is ring B, this is ring C, and this is 5-membered ring D. Now these two, 8th and 9th, okay, this 8th and 9th methyl group, they are called as the angular methyl group or angular methyl group. And this side chain at the 17th carbon, okay, this is the one of the side chain. So this is at 17th carbon, you will see one of the side chain. Okay, so this is our side chain. Okay, so to prove this structure of this cholesterol, so we should prove one by one for these things. Now what we have to prove, one thing, this structure of this cholesterol nucleus, this structure of cholesterol, it contains, or the skeleton of this cholesterol, it has 4 cyclic rings, 1 secondary OH, and one of the double bond is present. Okay, so what we have to prove in a structure, we will prove that 4 cyclic rings are present. Out of 4, 3 are the 6-membered, one is 5-membered. Then it contains one of the secondary OH group, it contains one of the double bond. And further we will prove the position of this double bond, the position of position of this OH group, and the nature and position of this side chain and at the last we will prove the position of these two angular methyl groups, that is at 18th and 19th. So what we have to prove? So I will prove, here I will prove, first we should prove the structure of cholesterol nucleus, and then we should prove this position of OH group and C carbon double bond, and then we will prove this position, nature and position of side chain, nature and position of side chain. Okay, and at the last we will prove this position of angular methyl groups, position of angular methyl group. Okay, so one by one we will take these steps. Now let's see first the structure of nucleus, how we can prove the structure of this nucleus. Okay, structure of nucleus, or what type of this skeleton the cholesterol has. Now if we see, then now first of all, the molecular formula for this structure of nucleus, the molecular formula of this cholesterol, that was determined to be C27, as it contains the 27 carbon atom, or it has a cholestein nucleus. It has a cholestein nucleus. In nomenclature I told you different types of the different derivatives of steroidal rings. So this is the cholestein nucleus. 27 carbons are present, and number of hydrogens here 46 if you will count, and one of the oxygen atom is present. Okay, this is the molecular formula that was determined by this elemental analysis and others. Now next thing, double bond equivalent. Now if we find the double bond equivalent, then number of carbon atom is 27, okay, minus number of monovalent atom, that is 46, divided by 2. Number of oxygen atom, we don't take it in a double bond equivalent formula, and there is no trivalent atom, that's why we will take just add it plus 1. Now here we will find that this will become 23, and this 28 minus 23, this comes out to be 5. So 5 is the double bond equivalent. Now you can already see that there are 4. It means the 5 corresponds to 4 cyclic ring and 1 double bond, which we have to prove. Now next thing that we will see, when this cholesterol is treated with when hydrogenation is done in presence of H2 and platinum catalyst, then it was found that the molecule which was obtained, that having the formula C27H48 and O. Okay, means number of hydrogen it is increased to 2 here. So this corresponds, it tells the hydrogen atoms are added along this double bond. So that's why it contains, therefore one double bond, one carbon CC double bond is present. So this experiment indicates that one carbon double bond is present. Now if this cholesterol that was treated with acetic anhydride, or we can say that if acetylation was done, then this converts up into the monoacetate monoacetate. So this monoacetate, it tells that it means one OH group is present, one OH group is present. Okay, one OH group is present. Now similarly, if we treat it by bromine, if we treat it by bromine, then that may give you the cholesterol dibromide. So it also tells the suppose this C27H2046O that was treated with bromine, then C27H46OBr2 was obtained. So this was the cholesterol dibromide. Cholesterol dibromide was obtained. Okay. Now, so means one double bond is present in a cholesterol and one OH group is present in a cholesterol. After that, this cholesterol that was treated with, as I told, this H2PT, and then what was obtained? It was giving H. Here we have methyl group, and here suppose I may write it HH. Okay. So this was obtained on reaction with this, on hydrogenation. This was obtained and that was named as cholestanol. Okay, that was named as cholestanol, and further it was treated with a chromium oxide. On treatment with chromium oxide, it was converted into this OH that was converted into keto group. Okay. Like this. So this was called as the cholestanol. And further, on treatment with zinc HGA, when it was undergone Clemenson reaction, zinc HgHCl, that is Clemenson reaction, then that was converted into this CO, this C double bond O, keto group converts up into CH2 here. Okay, say after Clemenson reaction, CO that would be converted into CH2, and you will get this one. Okay, now, so if we see, this is C27H46O. Now, the molecular formula for this cholestanol then becomes C27H48, because two hydrogens are added over here, C48O. Cholestanol, if we write the molecular formula of this cholestanol, then it becomes C27, okay, H. Now here if you see, then this OH is removed from here, and one H is removed from here, two H are removed, and this oxygen is added, and this oxygen is already present. So we can write two hydrogens are decreased and C27H46, and after this reduction, if you will see after this reduction, then here this oxygen is removed after reduction and two hydrogen atoms will be added over here. So this becomes C27H48. Okay, now suppose if I write, suppose this is 1 and this is 2, this is 3, and this is our fourth one. Now, so what it indicates? What does it indicate, this reaction? one of the thing, when it converts from 1 to 2, so this 1 to 2, so this indicates the presence of one double bond. So it indicates the presence of one double bond. Now 2 to 3, this reaction from 2 to 3, this indicates what it indicates. It indicates means OH is converted into this ketone. It means this OH, when the OH converts into ketone, when it is oxidized to ketone, alcohol oxidized to ketone, it means this alcohol is the secondary OH. So it means secondary OH is present. It tells the presence of a secondary OH. Now from third to fourth, it gives the fully saturated compound. This third to fourth gives the fully saturated compound. So fourth is fully saturated hydrocarbon. Fully saturated hydrocarbon having this formula is C27H48, and this it corresponds to the general formula. From this general formula is, what is the general formula? CnH2n minus 6. CnH2n minus 6 means 56 minus 48, that is CnH2n minus 6. So this CnH2n minus 6, this general formula, it corresponds to tetracyclic nature of this cholesterol. It means it contains, that is, it contains 4 cyclic rings. Okay, so these are the conclusions which are drawn from here. Now next thing that we may draw, that when this cholesterol, it was treated with selenium. Okay, next thing, when cholesterol C27H46O, when it was treated with selenium at 360 degrees Celsius and it is distilled, then we get the Diels hydrocarbon. So Diels hydrocarbon was obtained. Okay, so this is the structure of this Diels hydrocarbon, and the glycine was also obtained. Okay, glycine was also obtained. This is glycine. So this is Diels hydrocarbon, and this is glycine. So what does it indicate? This indicates that this cholesterol, it contains 3 6-membered ring and 1 5-membered ring. One thing, the conclusion from here, it contains 3 6-membered ring and it contains 1 5-membered ring. This it contains. And another conclusion that we may draw, that this glycine, it has the structure. This is the structure of glycine. Okay, so another thing that we may draw, at 17th position there is one of the side chain is present, because this Diels hydrocarbon, it contains the one methyl group at 17th position. So it also tells at 17th carbon may contain a side chain. So this conclusion can be drawn from this particular reaction. Okay, so from this structure of nucleus we have proved that it contains the 4 rings. Out of this, 3 are 6-membered, 1 is 5-membered. the presence of secondary OH group, presence of one double bond. So this has been proved by these reactions like this. Now, so this is the structure of nucleus. This is a skeleton. It proves the just skeleton of nucleus. Now let me prove the position of. Now we will prove the position of this OH and position of this double bond. So let's see. Okay, now second is the position of OH group. So let's see second one, position of OH group. Now how can we prove this position of OH group? So for this we may see one of the sequence of reaction. So let's see one sequence of reaction for this. So first of all, this cholesterol, that is C6, or let me write this cholesterol as this way. So this is our cholesterol, and when it was treated with H2 PT reduction followed by chromium oxide, and finally what was obtained? Cholestenol was obtained. So I may write cholestenol, this double bond is reduced by here, and we can write here this one. So this is our cholestenol. One keto group is present, that's why its name is as cholestenol. Okay, and then it was treated with, after this it was treated with HNO3. It was treated with HNO3. Now after this HNO3, presence of HNO3, if it is heated, then this keto group, that can be oxidized. It will undergo oxidation. Now after this oxidation, here the bond may be break. It may break either from here or it may break from here. So finally what we may get? We may get, suppose it breaks from here, then it is COH, and this is another COH, dicarboxylic acid, that was obtained. Or if it breaks from here, from this position, we may get this one also. Okay, further when it was treated, it is dicarboxylic acid, and actually it was 1,6-dicarboxylic acid. Okay, and further when it was treated with, when it was heated at 300 degrees Celsius, then a ketone was obtained. Okay, then a ketone was obtained. Now if we see its formula, then if we will see its formula, then no doubt it has C27H46O, and this has the formula C27 here. One hydrogen, these are two hydrogens are added here, and these two hydrogens are removed, so that's why it has the formula C27H46O. So as two hydrogens are added over here, in this formula, and two hydrogens are removed from here and here, that's why the formula remains same, number of hydrogen remains same, or the formula remains same for these both. Now, so if this is, suppose now first, this is second, and suppose this is dicarboxylic acid, so the formula for this C27H. Now if you will see here, then two hydrogens 2 hydrogens are added over here, whereas the 2 hydrogens are removed from here also. The 2 hydrogens are removed from this position. From here, these 2 hydrogens are removed and 2 hydrogens are added over here, and 2 hydrogens are removed from here. So formula C27H46O. C27H46O4. So this is the formula. And finally, the ketone which was obtained from here, that was having the formula C26. As you can see here, 27 carbon. This ketone was having 26 carbon and H44O. So this was obtained. Finally, the ketone obtained was having the formula this, molecular formula this. Now, so this is third. Suppose this is third and this is the fourth one. This is the fourth one. Okay. Now, what does it indicates? The formation of this cholesterol, 1,6-dicarboxylic acid and ketone. What does it indicate? So already I have told you from first to second. In previous case I have told you what does it indicate. Then from second to third, of formation of this second to third. So what does it indicate? Formation of dicarboxylic acid. One thing, if you will see, the number of carbon atoms remains same here. Here 27 carbon, here also 27 carbon. So as number of carbon atom remain same, so the keto group must be present. It should be the part of the ring, or oxygen OH is a part of the ring, we can say. So the keto group or OH group must be the part of ring. So as this dicarboxylic acid contains the same number of carbon atom, that's why the keto group should be the part of ring. It should not be the part of side chain. Okay, so it is not the part of side chain. Okay, so OH is not the part of side chain. So suppose if we consider that if it is a part of side chain, then what will happen? So suppose if OH is the part of side chain or keto is the part of side chain, suppose this is the open chain, it is not the closed one. So here the keto is a part of ring. Now suppose if keto is not the ring, it is open chain, then what we may conclude, if it breaks after this oxidation, then number of carbon atom, we will get the two product having the different number of carbon atom. So as this is a carbon atoms remain same, that's why it must have the keto group on the ring. It is a part of the ring. Now, so this is one thing. Now, another thing that we may conclude, that this keto, this formation of this dicarboxylic acid is suggests the presence of, or suggests that this keto group is flanked by, two methyl group. These are the two methyl group. This keto group is flanked by the methyl group. Okay, or it may contain this CH2COCH2 group. So it also tells, okay, so what we may write, it also tells that keto group is flanked by methylene group. Or it contains CH2COCH2 group. Okay, so if it does not contain this one, suppose if keto group is not flanked by this CH2, then what we may see, if keto group is not flanked by this one, then we may see that suppose it is something like this. Suppose if keto group is present over here, in that case it will not give you the dicarboxylic acid. Suppose it breaks from here, okay, suppose it may breaks from here, so it breaks from here, okay, then this dicarboxylic acid must be formed, or suppose it may breaks, this is one of the case, or suppose it breaks from here, then we will get this will form the keto, this will form the acid. So the dicarboxylic acid may not form in this case. So one of the thing was confirmed that this keto group is therefore present either at position, this is, as I told, this is first position, this is second position, this is third, and this is fourth, fifth. So keto group, either it is present at second position or third position. Either it may be present at second position or third position, so that we may get the dicarboxylic acid containing this group. Okay. So therefore, what it concludes? Therefore, the keto group may be present at second and third. So therefore, we may write, therefore the keto group, or we can say this OH group, keto group or OH group may be present at 2 or 3 position. So let's now confirm whether, that this keto is, or OH is present at at second position. So for this, let's consider one of the reaction. Okay. Now when this position, the second position of this OH group was confirmed by this particular reaction, when this cholesterol, when it was, suppose this is the cholesterol nucleus, when this cholesterol, when it was treated with Grignard reagent CH3MJI, then and further this hydrolysis, so what was seen, that this CH3 it acts over here, and this will go over here, and further hydrolysis that will be converted into OH. So what was obtained? It was seen that here we will have this CH3, this is OH, and clear. Now further, when it was treated with selenium at distillation, then Diels hydrocarbon that was obtained, having the CH3 group, at this third position. So this third position, this is important, but this is the third position. At this third position, this Grignard reagent was added over the third position. So addition of Grignard reagent at third position giving this methyl group here, and further the methyl group here. So that confirms the presence of OH group. So what it is may be called, this is dimethyl, these hydrocarbon, dimethyl cyclopenteno phenanthrene. This is our phenanthrene. Okay, this was the case. So for what we can write, the addition of Grignard reagent, at C3 carbon, and formation of suppose this is second, and this is third. And formation of second, third confirms the position of OH. Position of OH group as 3. Okay, so this is about the this OH group position. Now let's come to the position of carbon-carbon double bond. Now let us see about the carbon-carbon double bond. Position of double bond. Now, if you see this double bond position, then for this let's consider one of the reaction. For this, suppose this is our cholesterol, and when it was treated with hydrogen peroxide in acetic acid, then it will do the hydroxylation of this double bond. So it will do the hydroxylation of this double bond. So here one OH group and the OH group here. So this is the hydroxylation, and further when it was treated with chromium oxide, then it will do the oxidation. So this OH group, so if you cite, then this is third position, this is fourth, this is fifth, and this is sixth position. First, second, third, fourth, fifth. Now, so here this OH is converted into keto. This OH is also converted into, this OH is also converted into keto. This OH remains same. So further it was treated with, this was treated with this removal of H2O takes place from here. So this is the removal of H2O. So after the removal of H2O, the double bond comes over here. This is, and then this was further undergo reduction, zinc acetic acid reduction, and this double bond, it get reduced and further this was treated with again chromium oxide or this. Then what was obtained? So this oxidation occurs, and suppose this oxidation of this one here, this oxidation occur, and we get the tetracarboxylic acid. Tetracarboxylic acid was obtained. Okay, so now, so this was called as the polystyrene triol, and this may be written as the polystyrene. And this is tetracarboxylic acid of, so if we write, this is our C, if I write the formula, molecular formula, C27H46O. Now this is C27 H. How many hydrogens are present over here? So if we see, these 2 hydrogens are added over here. This is 48. Okay, 2 hydrogens are added at this position and this position, and 2 oxygens are also added over there. 48 C27 H48O. Now further, if we will see, then this becomes C27 H. So 2 hydrogens are removed from here. C27 H40. So 2 hydrogens are removed over here, and we are getting the keto group. 2 hydrogens are removed from here, we are getting keto group. So 4 hydrogens are reduced. So this is O3, C27 H44O3. Okay. Now this one. If you will see this one, then or if I write the formula of this one, and this is C27, okay, H46. Okay, 2 hydrogens. Now they are, this is one of the hydrogen, and this one hydrogen is added over here. Okay, and this is C27 H46O2. And finally this is C27. Okay, C27. Number of oxygen is here. Number of oxygen is 8. And how many is hydrogens? So if we add here this COOH, okay, so 4 hydrogens are here, are added. 4 hydrogens are added, and so this will becomes the C27 H44O8. Okay, so this will be the structure, this will be the final formula for this. Okay, now if we see when this cholesterol, when it was treated with, suppose hydrazine. Okay, when it was treated with hydrazine, then what was obtained? Pyridazine, that was obtained. Okay, so like this. So if this is our first one, this is second one, this is third one, suppose this is fourth one, this is fifth one, and suppose this is sixth one. So what does it indicate? So let's see what this sequence of reaction indicates now. So if we will see, then first of all, from this first to second indicates the presence of one double bond. First to second indicates the presence of first to second. What it tells? One double bond. One double bond is present. Now second to third, what does it indicate? This indicates the hydroxylation of, what does it indicate? It indicates that these two OH is secondary and one OH is tertiary, or this hydroxylation of double bond. So first it tells the one double bond, and this hydroxylation takes place. Hydroxylation of this double bond, and second to third it indicates there are here in third one, that is, or we can say in second there are two secondary OH group and one tertiary OH group. So this indicates two secondary OH group and one tertiary OH group is present present in second part. Okay. Now, this formation of this tetracarboxylic acid from 4th to 5th, if we see from 4th to 5th, this tetracarboxylic acid, it indicates that two keto group, these two keto group that are present in a different ring. So if, because they both have the same carbon atom, as 4th and 5th, they have 4th to 5th, they have same carbon atom, so therefore two keto group must be present in a different ring. So two keto group are in different ring. Okay. Next, the 4th to 6th. What does it indicate? It is a pyridine derivative, and this is formed between this alpha beta. Okay, this is suppose alpha beta gamma, or 1 2 3 4. 1,4 pyridine, this is formed. So the formation of 4th indicate that two keto groups are present over here, and this keto groups are, this is obtained after these different steps, and finally we can say that this to the double bond is present over this 5th and 6th carbon. So formation of the 6th, its formation indicate the presence of double bond at 5 and 6, of double bond at 5 6 carbon atom. Okay, so like this. So in this way we have proved the position of the double bond. Now let's see the position of this side chain. Now, position of side chain. So for this, let's take one of the reaction. So if we take this reaction where this cholesterol is, first of all, it was treated with acetic anhydride. So after its treatment, it will give AC over here, and okay, so this was obtained. The acetylation of this OH group occurs, and finally when it was treated with chromium oxide, then what was obtained? Here this bond breaks from here, and here the oxidation of these carbons will occur. So oxidation of this carbon and oxidation of this carbon. So this both carbons, these are secondary carbon. So as both carbon are secondary carbon, so after oxidation this will be converted into ketone, this will also be converted into ketone. So what we can write, OAC, and so this is the one of the, and another ketone that was obtained. This was obtained. So this is 1 2 3 4 5 6. This is isohexyl methyl ketone. So what was obtained? Isohexyl methyl ketone. So first of all, what we have done, acetylation of this is done, then chromium oxide, this was treated with chromium oxide. So and why first acetylation was done? Because if we do the chromium oxide oxidation, then this a third carbon. At third carbon also this OH would be converted into the keto group. So that's why first acetylation followed by this chromium oxide oxidation was done. So this formation of this second and third, so what does it indicate? Second and third indicate that this isohexyl, the side chain is present at this 17th carbon. The side chain is present at the 17th carbon, and the nature of side chain as well as the position of side chain. So formation of the second and third is keto group here, and formation of this cyclohexyl methyl ketone. So it tells the nature and position of the side chain. So formation of, what we can write, formation of the second and third tells the position as well as the nature of side chain and nature of side chain. Okay, like this. So in this way we have proved the this third part. Now let's come to the position of angular methyl group. Let's come to the position of angular methyl group. Position, this is fourth one, position of angular methyl group. Now position of this angular methyl group at 18th and 19th position, two angular methyl groups are present. So for this, the first of all, when the cholesterol it was treated with selenium, when it was treated with selenium at 360 degrees Celsius, distilled, then what was obtained? These hydrocarbon and glycine that was obtained. This is our D's hydrocarbon plus glycine that was obtained. So this formation of this glycine, or six-membered, four cyclic rings, which are six-membered, four cyclic rings are formed. So the formation of glycine, it indicates that this 18th carbon, the 18th methyl group at 13th carbon is involved in a formation of six-membered ring. So here this is five-membered ring. So this five-membered ring is converted into six-membered ring due to the presence of this angular methyl group at 13th position. So five-membered ring. So this indicates that the five-membered ring of these hydrocarbon get converted into six-membered ring in glycine due to the presence of this angular methyl group at 13th position, due to the presence of angular methyl group at C13 position. Okay, so we have proved the one of the angular methyl group. Okay, now another angular methyl group is present at C10 position. So for this, so let's see the position of this another angular methyl group. So for this, the reaction that was taken when this cholesterol, when this cholesterol was when it was treated with, okay, when cholesterol was treated with here H2PT and further chromium oxide reduction, chromium oxide oxidation, then here we get the double bond, and finally this is one of the angular methyl group, and like this, and further chromium oxide reduction, so we will get the, here we will get one of the this COOH group, and here's keto group. So actually 2 times this oxidative degradation will occur to get the keto group over here, and further, okay, further that would be again 2 times chromium oxide oxidation in presence of H2SO4, that is also called as the Barbier-Wieland degradation. Okay, so this gives, what does it gives? It was giving the one of the COH group over here. After the degradation, this COH group was present over here, and okay, so now further when it was hydrolysis was done, or when it was treated with esterification was done, further esterification, then it was no esterification of COH group occurs. So no reaction after this esterification. Means this COH group doesn't undergo esterification. So why? Because this COH group here, it is present over the tertiary carbon, and this tertiary COH group is not easy to. The rate of esterification of secondary tertiary COH group is very low. So that's why it must be there. One of the methyl group must be present over the this C10 carbon. So the since the this esterification, no esterification occurs here, so it means since no esterification occurs, therefore the COH group must be present at tertiary carbon atom, and therefore OH group or methyl group, angular methyl group must be present at C10 carbon atom. Okay, so we may also see that after this reaction, as this Diels hydrocarbon, it contains 17, these are the 17 carbon nucleus. This is 17 carbon nucleus, and one of the side chain, it contains that side chain has the 8 carbon atom. So it means there are total 46 carbon, and out of there are total 27 carbon, and out of this 27 carbon, 17 carbon it corresponds to this Diels hydrocarbon, which is one of the part of this cholesterol, and 8 carbon atom is for this side chain. So 8 carbon for this side chain. Okay, so 1 2 3 1 2 3 4 5 6 1 2 3 4 5 6 7 8. Okay, so that's why total number of, if we will see, then it is 23 minus 27 minus 25. So 2, it corresponds to 2 angular methyl group, and one angular methyl group is, this is one of the angular methyl group at this position, which is involved in the formation of which is involved in the conversion of this 5-membered ring into the 6-membered ring, and another is present at this C10 carbon, which is proved when this sequence of reaction was giving a COH group over here, which cannot be further esterified. Okay, thank you.